really have a choice.
I love that.
Yeah.
I always remember that my dad. So like, yeah. I am allergic to nuts,
put
so
up,
I have to be careful with this.
Slides. I put
So
up
you
chapter
really
3
don't
and chapter 4.
know.
And we're at chapter 2 now.
Also the dark chocolate.
No, it moves to where you're talking. That's so really makes it.
Yeah, it does.
Should we turn it? Can she see the board? Or do we have to?
No, I have a share screen.
Oh, you're sharing screen. Okay, fine.
Okay. Yeah, this system structure is improved but not invented. So to describe this, okay, this is the objective. To describe the services of an operating system, we kind of discussed this. To discuss the various ways of structuring an operating, to explain how operating systems are installed, customized, and how they boot. This is like we're still kind of in introduction. I have to say that like even until chapter 4, we're chapter 4 is the beginning of the real material, I would say. So I'll try to go as fast as I can. So there's two types of user interfaces. One is a command line interface, which is what we did in the lab. Remember we had like a black screen and that's called CLI or command line interface. And then there's also a GUI or GUI or graphic user interface. It's also a way of talking to the operating system. For example, if you have a task manager in Windows, you can turn on and turn off processes. People know what task manager is?
Yeah.
Yeah, some people know. Well, you can if your program hangs, not
What's the
It's
graphic
stuck.
interface do?
graphic interface is just a way of interfacing with the operating system. There's two. You can either interface on command line or with clicks and buttons. And that's a graphic line. The system must be able to load a program into memory. These are things that the operating system has to be able to do. And run a program. How do you run a program, by the way? In the command line, basically what you do is you type the name of the program and hit enter. Assuming that you have the path. In other words, the path is where it is on the disk. So for example, it could be in a folder, and is that another folder, is that another folder? You have to know which folder it's in, and then you go to that folder and you click on it. Clicking on it is the same as hitting enter. Clicking is how you do it on a graphic user interface. On a command line interface, you hit enter. Either way, you'll run the program. The program has to be, of course, runnable. It has to be either a binary that's been compiled, or it could be a interpreted program. We don't talk about that now. I/O operations. A running program may require I/O, input output, which may involve files or an I/O device. Right? That's what, in other words, the operating system has to provide you, so services again, has to provide you a way of accessing files or hardware, like a screen.
That's the IO system.
That's I/O, input output. File system manipulation. It has to let you create, delete, move files around, right? You have to be able to delete files. These are all kind of obvious things. I think if you would just sit down and write what an operating system do, you could probably come up with this list. These are just the obvious things that an operating system has to do. It also has to have communications, which we're going to talk about. IPC. IPC is inter-process communication. It means a way for the processes to talk to each other, to pass information from one to the other. This can be done via shared memory or through pipes. Pipes are just kind of like a file. A file, you could theoretically have two processes write to a file, one write to it, one read from it. So that they're communicating by writing and reading from the same file. But a pipe is similar to a file, but it's a file in memory, essentially. In other words, it's like you create a file, but not on the disk, just in raw memory.
Wait, IPC is inter-process communication?
Inter-process.
Inter.
Error detection. The operator needs to be constantly aware of possible errors. Memory I/O device could have an error, right? But it can't read or write to a certain sector of disk. The operating system should have a way of dealing with that. Like, for example, marking a section of disk is unreadable and then knowing to skip it and not use it. Debugging is also the job of the operating system. It's allowing the debugger to work. The debugger needs to have certain, in other words, how does a debugger work? You step through a program, right? You stop it after every execution. That's it. The operating system has to be able to do that for you. More things that operating system does. Resource allocation. Well, we talked about that actually. In other words, the fair distribution of resources. CPU is the main one we can think about. Many processes are running on a computer at the same time. They all are fighting to get the CPU, to get the computing power of the computer. Somebody has to be the like a parent in the room. Everybody gets an equal share of cake. Somebody has to divide up the resources in a fair way. But that's just one resource. There's also resources of disk and other things. Memory, accounting, to keep accounting, which is to keep track of which is what use how much and what kinds of computer resources. If or I'll give you another example of accounting. Let's say you want to know how often has the CPU been busy? How much has it been busy? Let's say I want to know, do I need a new computer? How am I supposed to know if I need a better CPU? I need to be able to have some kind of statistics on how often, how utilized the CPU was. Or if the computer is running slow, and you want to be able to know, is it because the CPU is overutilized or because there's not enough memory? Right? There's two possible reasons why a computer would run slow. So there needs to be some kind of statistics accounting. And then protection and security. If you have multiple users on the same computer, each one should have their data secure from the other. I shouldn't be able to corrupt somebody else's files. Security also from outsiders, and also between processes. One process shouldn't use the memory of another process. Well, that's similar to what I said about allocation. Okay, so here is a generalized view of an operating system. And you see, if you look at the bottom, too small, I think. So, is the camera going to follow me? No. But here's the hardware. And here is, well, I guess all of this is the operating system. I'm not sure how this is diagrammed. Yeah, I guess all of this is the operating system. And then this is user and other system programs. So inside of the operating system, which is between the hardware, in other words, it allows communication between the program and the hardware. So the most basic thing it does is what we just described. It allows program execution, I/O, communication between processes, allows access to the files, to the disk, resource allocation like CPU. Resource allocation is referring to CPU and memory in general. There are other resources. Accounting, all those things are services to the operating system. Then there's a system call. See, when I want this service, I have a special function that I'll call a system call, which will give me that service. Now, I want to open a file. So I'll have a system call, which will open a file and give me access to the file system. So these are like the primitive services that it provides. But when I interact with it, I will interact with the operating system using system calls, which are essentially functions in C functions. And then you have, a command line. Let's say I want to say open a file, it might be a command line. The program that deals with this command line will call a system call. There's three layers. There's a command line like on our click of a mouse. Then when I click that mouse, that's gonna run a function or a program, and that program will call a system call to give me the service that I want. That's better. You know, I probably should show you what I'm talking about. Well, I'll show you in the lab. I'll show you in the lab. What is this? Right. So in the command line interface, you can do things like CD, which would be change directory. Move you around in the directory tree. Or you can do things like touch and then a file name. Touch is a command that creates a file. So you type touch and then your file name, myfile.c. And then you created a file called myfile.c because touch, that is a command. It will call a system call, which will be open. The system call is called open. And that will open or create a file. Okay. What is this picture showing?
Where can we find all the commands?
Well, they vary from operating system to operating system. They're more or less the same, but they are not exactly the same. So you'd have to choose the operating system, like Linux, and then you would go to Google and type basic commands. Google Linux basic commands, and then you get a list of basic commands. That's the best way. There are like cheat sheets, also Unix cheat sheets, where you have like a whole list, like a one page with a whole list of many commands and a short explanation of what they all are.
Do we have to know the commands?
For this course, no. In third year, there's a Unix course that you. I don't know. Yeah, this is just showing an example of like somebody typing a command W, which it's really short for who, WHO, and it shows you like who is on the machine. So it shows you the console. I don't know. Who, the user is named PBG. That's a funny name for you. That's his name. And then you can do IOStat, another command, IOStat5, which will show you various statistics about the computer. CPU usage, disk usage, load average, all kinds of use statistics. All we were talking about before about should give you statistics, it should give you counting.
You recording this or it's?
I'm recording.
Okay.
And LS is just to list all the commands. So these are just like various command line interface commands that you could type on a Linux machine. And it will do operating system, it'll request system calls. Okay. User. So GUI, you're all familiar with the GUI, that's just that you can click on pictures, and that's the operating system. The operating system is a Windows operating system, means it has windows, it has buttons and things. That's another way of interacting with the operating system. Many systems now include both CLI and GUI. Like somebody was asking about Macintosh, or Gabrielle, you were asking about Macintosh. So Macintosh is a GUI, but underneath the GUI is basically a Linux machine. I don't know exactly what kind of Linux, but it's a kind of Linux machine. So if you just make a console in a Mac, you will have a direct access to the operating system or a command line access. Windows is not, but Windows has more and more adopted all kinds of Linux styles. Here's a touch screen interface. It's also an operating system. Well, you know that from your phones. Here's a Mac OS X GUI. System calls. Okay. System call typically written in a high-level language or C. I don't know if you remember, we did in computer architecture, we did like we wrote system call, and there was a number that we put into a certain vector, into a certain register.
You had to know the.
And then you had to know the number, and then that's a pure system call. In other words, there's a table of system calls, you tell it run system call and it checks the number in a certain register and it goes to the table and does the action that's supposed to do. Now, that's a very inefficient way to, or inconvenient, I don't know, inefficient, it's efficient, but it's not humanly, not user-friendly way, it's not a user-friendly way of doing system call. So therefore, we have these high-level languages, C or C++, you'll have a system call be written in C, which will essentially do the same thing. It'll call that underlying methodology, but you'll write it as a function, as like a normal function with parameters. So it'll be a name of a function, parentheses, parameters. I want to take an example here. Yeah, here. For example, here, read. Read means to read data from a file or the screen. So look, it takes three parameters. FD is the first parameter, that's where to read from. For example, the screen or the keyboard. Well, if you're reading, you would read from the screen. So the keyboard or FD could also be a file. Read from a file, read data from a file. Now, if you're reading data from a file or from a keyboard, you have to read it into something. You have to read it, it goes somewhere. When you read with your eyes, it goes to your brain. When you read in a computer, it goes into something, it goes into what's called a buffer. You have to have a buffer of characters, a long character array that you read into. So that's this buff. Notice it's a void pointer because you could read either integers or characters. It's written in a generic way, this function. So that it could take any type of pointer. That's the buffer. And then the size T count. Size T is really just a size type. The T means type. It's a size type. It's essentially an integer. So size T is how big is your buffer. So that is sometimes that's a standard API. It's complicated here. Most people will refer to this as a system call. In fact, I would refer to this as a system call. But technically it's not. It's an API call. You know what API stands for? Application Programming Interface. So you always use, when you want to use somebody else's program or somebody else's library, you say, I'm going to use their API. That's the way you refer to it. Their whole interface, their whole framework. So this is an API call. In other words, this is a C program, a C function, which is itself a wrapper to the underlying system call. But since it's the underlying system call would be just like putting a number in a vector in a register, like you did. So, but we call this also a system call, but technically it's an API call. It says why use API rather than system call? Portability. So you gain portability. What does that mean? What does portability mean? Do you know what portability might mean?
Portable.
Yeah, portable. Portable between what and what?
User.
No, answer. Portable means that if I have a new version of the operating system, which is stable, or a new version of the hardware, I'll say better, hardware, the hardware changes, and no longer is reading by number 7, it's by number 8. So this function will stay the same. In other words, the person who wrote this function will write a new version of this function for the new hardware, but I, as the programmer, will be able to run all my programs that use this function, read, just as I did before. As long as the API was updated to reflect the new hardware, that's what portability means. I mean, portable between different hardware. In this case, portable could also mean between different operating systems. That's the term. The term portability means that it's like, you know, it's multilingual. That's what for human beings. Okay. All right, I just explained this. This is typically a number associated with a system call. That's what I was explaining. That's what you know. Okay. We talked a little bit about this user mode and kernel mode. This is a very weird concept, but we talked about it, that an operating system is also called a kernel. So kernel mode would be like operating system mode. What does that mean? That means that it has access to all the most high, how do you say, top secret, behaviors. That's a metaphor. Not top secret, but things that are reserved for all the operating system to do. So they can only be done in kernel mode. So your process that your program, when you run it, is a process. And so you do various commands, and then eventually you call a system called like open. And that's your system called interface. He now will have to switch into kernel mode to actually do you'll switch your process into kernel mode. Then your process will do these restricted actions. And then he will take you out of kernel mode at the end of the system call. So for most people would think mistakenly that because the way we talk about it a lot is, the operating system does this for you. The operating system opens or creates a file for it. But a more correct way of saying it is it deputizes your process to then your process to do. And then takes away that deputization when you're finished. So actually your process is doing the opening of the file, but it's been deputized. I invented that term. In other words, we usually talk about a human being, but like deputized in the sense, you're now like on the level of the operating system. You can do all those restricted things, but in a limited way, only the thing you requested. Okay. Right. Often more information is required than just the system call number. Well, that's kind of what we saw over here. I said that this read here has a void pointer because it can read any type of data. So I need to tell it what type of data, and I do that by in C++ by casting. I'll cast that void pointer to whatever type I want. Yeah, this is too much detail. I don't want to get this. Okay. Now it's just a list of types of system calls. Kind of boring, but load a program, execute a program, create a process, terminate a process, wait for time. As you can do that in C++, you have a function called sleep. In C. In C on Linux, you have a function called sleep, which puts your process to sleep. Now it doesn't do anything for a certain amount of seconds. So we wait, or wait for an event. You can say put the process to sleep until his child process returns with a value, sends him a value, gets a message from his child process. Dump memory of error. That's another thing that will happen. For example, your program crashes. Something called a core dump. It will dump all the values of the memory from your remember your process is allocated a certain section of memory, not the whole memory of the computer, a certain section. When your program crashes, you can dump all that memory into a file, and then you have a core reader, which will tell you what all the values of all the data was in your program at the moment of the crash. And people may want to look. You may want to look at that to see why it crashed. You want to say, oh, it was this. The program counter was at line 50. Oh, that's interesting. What was that register? It tells you all the registers and all the things that the program. Hey, you gotta mute. Wait, we lost Alicia. Okay. That's another thing that operators can do. File management. Well, this also I hope is obvious, like create files, delete files, open files, read files. Device managers, what is device management? What is a device? Anyone guess what a device is? We mentioned it before. It's a device.
Mouse.
Yeah, hardware, any kind of hardware. And you're going to read and write to devices, which could be the screen. I always like my examples, the screen and keyboard. Every computer has those devices. Not every computer has a fingerprint reader. But those are also. Okay. Information maintenance, get time or set time. the program, the computer knows what time it is. You have to be able to, the operating system takes care of that, it'll set it. Communications, create, delete communications. Now there's message passing. If you have multiple processes, they need to be able to communicate. The operating system has to provide methods for communication.
If there's multiple what?
Processes. Protection, control, access to resources. So for example, my file should be limited to me. We talked about that last time in the lab. I could change mode, where you have a mode 777 is the world, everybody can access it. So control access to resources. One example of resources of file. Permissions, that's what I was talking about. Allow or deny access. Okay. Users, right. So you can say a certain user can't log on. You can cancel his log on. His account can be disabled or enabled. Or you can create a new account. Those are also things that an operating system has to provide. The ability to have multiple users. Right? If you think about it, go back to basically what an operating system is the difference between your MIPS simulator, what you could do there, and what you and everything and a modern computer and a whole computer. A whole computer allows you to have logins, allows you to have create files. Like how would you have logins in MIPS? No logins. Just turn it on and you're there. Examples of Windows and Unix system calls. Again, this is just a list of function names. You don't have to remember this, but read file, write file, sleep. I mentioned that one. These actually shouldn't be capitalized. I don't know why. Oh, this is Windows. These are the Windows names for the and it's the Unix names. So sleep is capital S for sleep in Windows and lowercase s sleep in Unix. Pipe creates a pipe in Unix. In Windows, they call it create pipe. So you see, anything you learn in Unix is the same thing in Windows, just the name is a little different. Read console. We just call that read. I mean, when I say we, because I'm from the world of Unix. So I would call it read, but Windows calls it read console. Create file, we just call that open. We don't have a function create, that can be confusing. Open creates. It also, because open is a dual purpose function, it also opens a file that already exists. But if the file doesn't exist, then you can tell it create. Then you have a flag, a parameter that tells it whether you want to create it if the file doesn't exist. So open is a dual purpose, so they called it open, and Windows called it create. But I wonder how they open a file. That's an interesting question. Maybe create has a flag to tell you not to create it, but the open is. Anyway, these are systems. See here, look, I just want to show you the confusion that even the slides have. Here it calls it Unix. Examples of Windows and Unix system calls. So these are system calls. But hey, wait a second. 10 slides earlier, it said these are not system calls. It said these are API calls. Remember that? I said the API calls are just a wrapper to a number that you call, like in MIPS. Right? If you go back, here, example of standard API, and it's read. And look, come down here, and here's read again, and it's now calling a system call. Because there's a certain confusion, I don't want to say confusion, but conceptually they're very similar. It is really a system call because it is directly calling that system call, but it's not the system call. It's an API wrapper for the system call. So here the slide's calling a system. Just, I mean, these are subtleties of terminology. Standard, here is an example, printf. There you go, that's your C out from C++. In C, we write printf. And actually, now they're telling you even more confusing thing here, because the printf is even a higher level API. It's also an API call, which calls the printf, which calls the write command. The write function will be the system call, but of course the write system call is not really the system call. The system call is really on the level of putting numbers in registers. So there's like 3 levels. On it all, printf, which is like a more friendly version of write. Then there's write, which is the system call, quote unquote system call. And then there's the real system call underneath the write. So here they're calling write a system call, but before we call it API. Okay, that's so important. I'm just pointing out, you should understand that there is a lot of levels of wrappers. Printf allows you to format the text more. It has all kinds of extra features which do not exist in the underlying write function. Now here's talking about programming environment, and I'll just skip to some of the important ones. GCC is the compiler. It stands for GNU, G-N-U, which is an animal that lives in South Africa or in Africa, right? GNU, or GNU. Also called the wildebeest.
That we know.
What does it stand for?
You're also South Africa? No. You're also from Macintosh. Okay. A wildebeest is like this animal with this funny horns, and it's also called GNU. And I don't know, for some reason, Linux programmers were enamored with this animal, and everything they call GNU is like, that's the organization that makes like free software, open source software is called GNU. So this is the GNU. I don't know if you pronounce it GNU, but anyway, it's maybe just pronounced GNU. It's GNU. But the GNU C compiler, that's what GCC stands for. And that's a compiler. So if you want to compile a program, it would be nice to have an example here. There we go. Okay. But if you wanted to compile a program, you would type GCC space and the name of your program, myprogram.c, and you hit enter on the command line, and it would compile. Now, what does it mean to compile? It creates another program, another file, which has by default is called a.out. And then that file is executable. It's actually a runnable version of your program was in a high-level language, C++. That a.out is going to be in machine level. It's a binary file. It's not an ASCII file. If you try to read it with a normal ASCII file reader like Notepad or any other program, it'll look like gibberish because it's not in ASCII. It's ones and zeros, but it's not in ASCII. So ASCII is also ones and zeros. But an ASCII reader like Word or Notepad knows how to present those ones and zeros as letters. But if your program is ones and zeros that are not representing letters, right, the ASCII code is in a certain range, but they could be the ones and zeros are different numbers. So then it won't be able to present it, it'll look like gibberish. But what it actually is the compiled binary version of your program. That's what's the job of the GCC is, to turn your C program into a compiled version, which you can then run by typing enter. Press enter on the name of it. You write a.out, enter, and then it would run. You
Wait,
can also
so turn a C program into what?
into a binary machine language program. So this is actually technically not really part of the program. It looks called a system program. When I installed Ubuntu in my video last night, if you looked at it, I looked at it last night, but whenever you looked at it, you'll see that I tried to compile something and I don't have the GCC compiler. So I have to download it. So actually, the operating system was installed, but without this program. This program is not part of the operating system. They call it system programs. It's kind of like, I don't know, I would say it's a basic programs that are in addition to the operating system that need to be there. And you need to have a compiler because anytime you're going to want to, what do you do with a computer? You program it. So you need to have some kind of compiler. So also, now these other examples, SSH is also not necessarily there. What is SSH? Anyone know what SSH is?
Does it have to do with like accessing remotely?
Yes, that's with accessing remotely. It allows, SSH is a program that allows you to, access a remote computer. You type
Security encrypted connection.
Yes, it creates an encrypted connection to a remote computer so that you can now perform actions on the faraway computer. So that's also not necessarily essential to the operating system, but it's a rather basic need. So it's a software, there's system program. There's a program that's like, well, system programs provide a convenient environment for program development and execution. So in other words, they provide they're convenient, and as we need them, they're useful, but you don't necessarily have to have them. Since most users' view of the operating system is defined by system programs, not the actual system call. As most users don't start writing programs with open system calls like we just did. Although we're not most of them. There are other, okay, now it's just like, I don't know, other programs, file creation, these are other file management system programs. Also, system programs to tell you the status of your computer. Let's just go on.
I think you're like, oh, this is important, that's not important.
Well, this is, like I said, this is an overview. I mean, I might ask you, give an example of a system program, you know, in the Linux operating system. I might ask you something, but I'm not going to ask you too many details about it. Yeah, because we're going to get into more theoretical stuff. This is like an attempt at the court. Even this is theoretical, but this is actual examples of what things there are on an operating system. The course is going to become more talking about algorithms. You know what understand what algorithms are, right? Like algorithms for how an operating system makes its decisions. How does it decide who gets the CPU now? This is still like whatever user should really know, not the theory. This is like these are programs that exist. So it's not less important for this course. This course is really more about the theory. Okay, quick questions?
Yeah, what's the difference between a compiler and a program?
Well, a compiler is a type of program, but a compiler is a program. Somebody wrote it and compiled it with another compiler. A compiler is what turns a program in a program in a high-level language like Java, Python, C++ into a machine-specific machine language program. What you wrote in architecture was assembly, and then there was a kind of a compiler that turned the assembly into ones and zeros, which is called an assembler. It's not technically a compiler, but it's similar. Okay, let's go on. Well, this to me seems like it's repeating kind of what it did before, except it's saying, just like the operating system has to provide communication, so there has to be a system program to provide communications. Program load and execution, right? You need to have a way of loading into memory your program and then running it. There's a function, a C function called exec, which is short for execute, which is how you run, which loads and runs the program. There are also background services. I'll give you the best example of background service actually is SSH. Remember we talked about SSH? It's for connecting to a remote system. Well, let's think a minute about that remote system. I write SSH to my computer in Hawaii. And now I'm there. But that computer in Hawaii has to be plugged in, turned on. And not only plugged in and turned on and connected to the internet, it has to also connect to the internet, right? And not only that, it has to have a program called SSH running. So that my SSH can communicate with that SSH. And my SSH will be an SSH client. I will be being a client to him, but he will be a server. What does it mean he's a server? He is sitting, I'll give you a mashal. Mashal is like a beautiful girl at the ball. She sits there and drinks her tea. And then the men all come and ask her to dance. She doesn't move, she just sits there, they all come to her. Yes. So, and then if somebody comes, maybe she'll dance this one, she'll dance that one. But she is sort of like waiting. But she's ready for people to approach her. So that's what a server is. A server is sitting there waiting for SSH connections to appear. And if somebody wants to connect to the server, then either they'll grant permission or won't grant permission. That'll be the server's decision. But that means there has to be an SSH server sitting there. So a server will have many services running. And a good example is an SSH server. And why am I mentioning this? Because it's running in the background. It says here background services. What does it mean it's running in the background? If I log on to the server, I don't even know that. Notice if I'm sitting in front of the server in Hawaii and I'm typing on, I don't even know there's an SSH program running. It's not even interesting to me, but it's running nonetheless. It's running in the background. It's not occupying the screen. I don't have any output. I don't see anything, but it's allowing other people to connect to my server. So it is running, but it's not running in the foreground. It's not taking up the screen. It's not interacting with me. It's running there to allow others to connect to my machine. There are other types of background services. Well, many of the services that we'll talk about later in the course are background services. Like, for example, something called the scheduler, which is the program part of the operating system that decides to schedules. It's like it does scheduling. Who gets the CPU first? Who gets it second? Who gets it third? Deciding which processes get the access to the CPU is the job of the scheduler. But he doesn't run in the foreground. I don't see output from him all the time. He's running in the background and I don't even notice. But then there are application programs like Word, not typically considered part of the operating system. Okay. So this is a famous question that we always talk about in architecture, in computer design, which is how, when you design bridges, there are books about how to design bridges. And we kind of know how to design a bridge. And if you want to build it this big, we sort of have rules and how much cement you need and how much steel you need. But there's no clear rules for how to design an operating system. Neither are there clear rules for how to design a piece of software, any program. So that's what it says, not solvable. That's what I mean by not solvable. Design and addition operating is not solvable. There's no solution that's the correct solution. There are considerations. I may want my computer to run a little bit, slower because I have other considerations that I want. In general, we want the computer to run as fast as possible, but the types of uses that we have for our computer may vary, and that may affect the design. But user general goals are that the operating system should be convenient to use, easy to learn, reliable, safe, and fast. These are key words. Reliable, what does reliable mean? That it doesn't crash. Safe, what does safe mean? That my programs don't get corrupted by other programs. Fast, well, faster than fast. System goals. Operating system should be easy to design, implement, and maintain, as well as flexible, reliable, error-free, and efficient. Flexible means they can run different kinds of programs. Reliable, I don't know what the difference. System, I don't know. These are user goals and system goals. In other words, the first one is the user's perspective. These system goals are what the system designer is going to think about, which may be slightly different from what the user thinks. Because he's going to think about it should be easy to design. The user doesn't care how easy the design was. He just cares that it works fast and doesn't screw up the program. But as a designer, I prefer a simple design to a complex design, because a simple design will be easier to maintain and to alter. You heard that KISS? Keep it simple, stupid. We want to have things simple. Okay. How much more of this? See, that's why I go fast. We got a lot of stuff.
Topic conversation, or just like generally? The course in general, is it going to be like more like introduction to an operating system, or is it like topic by topic?
So we're going to go, this is still, I would say the first two chapters are really introduction, then we're going to get into some specific topics. important principles to separate what will be done and how it will be done. So, right, policy is what we want the system to do. The mechanism can be different. In other words, I mean, you could do this on many levels, but we're talking about, this is a general design question. In other words, what do we want to do? We want to build a house with, 4 bedrooms and a bathroom. I don't know. The mechanism, how we do it, we could build it with concrete walls, we could build it with plaster walls, we could build it out of bricks. The method, the mechanism, how we do it is a different question. So if I want in my operating system that there should be, scheduling of processes to the CPU, that they shouldn't all fight, they should have a certain person, certain process deciding who gets the CPU. So, but how do I do that? How is he going to make these decisions? It could be different. Or whether that, whether I'll have 2 processes doing it or one doing this, like that, maybe several processes being scheduled. All those are like how I'm going to do it. But the policy is what I want to be done. Maybe the policy will also affect how I do it. But the policy is the goal, and the mechanism is how I'll achieve that goal. And sometimes the mechanism, I don't care about it. Sometimes maybe I do care about it, but I may not. It's important to make this distinction. Because a lot of times people think, I want to do it this way, and this is the mechanism I want to do it for. This is the way I want to do it. And they think that, in other words, they have to decide, wait a second, do I really want that policy? And is that the only mechanism? Maybe there's another mechanism. Maybe I want a different policy. Maybe I want that mechanism, a different policy. It's important to distinguish these 2 things when you're designing anything. These 2 aspects, which is your policy, your how I want the system to work, and the mechanism, how to accomplish that way of working. Mechanisms determine how to do something. Policies decide what will be done. Okay. So now we're talking about implementation, because you could write your operating systems straight in machine language, and that's how they originally did it, in assembly. You write it in assembly. Nowadays, we write them in languages like C or C++. Unix is written in C. In fact, the language C was invented for the purpose of writing the operating system Unix. The same people who invented Unix invented C, not the precursor to C++. But here he says actually usually a mix of languages. The lowest level parts of the operating system may be written directly in assembly to be more efficient. Then the main body of the operating system will be written in C, and then some system programs will be written in maybe even C++. Okay.
What do we mean by scripting languages?
What?
What do we mean by scripting languages?
Scripting languages, well, those are languages that are not compiled. That's the technical best definition. In other words, you compile a language into ones and zeros, and then you just run it. The machine knows how to run a compiled language. A scripting language, you have to have an interpreter running in the background. And then when you run the program, every time you run it, he'll read the lines of English that you've written and turn it into compiled into a compiled version as you go. So it's like an interpreted language supposed to compile language. But there's different languages. If you learn Python is a scripted language. Shell script is a scripted language. Perl we don't learn anymore. Also PHP. I would change this to PHP. Okay. General purpose operating systems like Windows and Linux are very large. There are various ways to structure them. One as follows. We're going to talk about monolithic. There's a concept called a monolithic operating system and a modular operating system. So we'll talk about that. Unix is limited by hardware functionality. The original Unix operating system had limited structuring. The Unix consisted of two separable parts: system programs and the kernel. The kernel is really the operating system, but the system programs were like an addition to it. We listed what system programs were, like SSH or GCC are system programs, but they're clearly separate from the operating system. But everything else, the scheduler and all the things that the underlying operating system has to do, was all in one large program called the kernel. Everything below the system called interface, in other words, the actual system calls, would be in the kernel, above the physical hardware. Here's the things that it would do: CPU scheduling, memory management, other operating system, a large number of functions for one level. In other words, this is a kind of criticism. There was a lot of stuff that one program was doing. The whole kernel was, we call that a monolithic kernel. One program that was the whole operating system. Monolithic means, well, Neolithic is the new stone. Lithic means stone, right? So monolith is a single stone. In other words, a single, it really should be called not monolithic, but mono program. Monolithic, I guess in English means singular.
So it's one program, that's the whole operating system.
Yes, that would be a monolithic.
That's like not good. It's not smart.
Well, it has advantages and disadvantages. Remember, this is actually why we said this first thing about this a separate policy for design. You get the same policy, right? You're going to get everything you want. So but the mechanism is a what. There are some advantages to having it in one program. It might be faster. It might run better. But the disadvantage will generally be harder to maintain. If I want to change one part of it, I've got to figure out all the places that part is being implemented, as opposed to a modular operating system where there are certain modules, where one module does one activity. And then if I want to change that activity to a new way, then I just change that module, and I know where all the program that deals with that is located. So there's advantage to this. The advantage is that it might be faster. So here's the kernel. Beyond simple but not fully layered, consider. Oh, actually, so he's a little bit disagreeing with me. He's saying this is not monolithic. He didn't use the word monolithic here.
He said considered monolithic.
No, here he didn't.
Oh, where?
The original operating system had limited structure, two parts, system programs and the kernel. Now, he calls this monolithic, but this is also, there's all this system.
Isn't it the exact same thing?
It's pretty much the exact same system.
So he's just contradicting himself.
No, there is something, you have to think about what, maybe here there's terminal control and device controls. Maybe this is outside of that, maybe they, okay, that's the main difference. The main difference is that this is the way it is now, pretty much. The terminal controllers and the, let's say, device controllers, the disk controller, the tape controller, the keyboard controller, memory controller, controls of the computer memory, all those are maybe separate from the kernel. Those are separate modules. They're separate sections. So in a sense, it's, I don't know why he calls this, but it's still monolithic because the essential kernel is monolithic. These device components are not really part of the operating system. Let's see. There's also this layered approach. Here, I think I added a lot to the slide. Whereas a monolithic operating system is an operating system architecture in which the entire operating system works in the kernel space. Right? Now, there's anything that the operating system does is doing as kernel, in kernel mode, let's say. A layered operating system is an operating system architecture that's divided into a number of layers, each layer performing a specific functionality. With modularity, layers are selected such that each uses functions and services of only lower level layers. In other words, that's the key point. What makes it layered and not just different sections? Here's modules. Here's modules. We're going to get to that, but we're talking now about what does it mean that it's layered? What's the definition of layered? So the real definition of layers, you can say, well, it has many layers. What does that mean? It's layers. What does it mean just different parts? What's the difference between a part and a layer?
They build on each other,
What?
layers build on
They
each other.
build, layers build on each other, and what that means in the words of what's written here is that if that layer one only communicates with layers beneath it. Because when I'm building layer one, essentially layer one doesn't know about the existence of layers 2, 3, 4, and 5. Layer 4 only can deal with itself and with layer itself and layer 3, 2, and 1 and 0. It's each layer I can essentially develop on its own and finish before I progress to the next layer. There's no upward movement. It's always going down. Every layer communicates to the layer beneath it. I don't know if people understand why that's important. That's good. That's very good and very important because why is it good? Because what?
Security, like private, like the.
No, that was for design, for ease of design. In other words, I have this huge program that I want to write. How am I going to write? You guys have written short programs, You haven't had to design a huge program. How do you design a huge program? So first you say, well, what's the essential things that I need? And I'm going to do those. And then who's going to use those things? Everybody else is going to use those functions that I built. First, I'm going to start with the functions that are used by everybody. And those will be the level 0. And then I'll start with more functions that are used, that don't use those lower level functions to do more complicated things. And then somebody may want to use this new layer. If I build layers by building a set of functions that provide a certain level of service. And as I want more and more complicated, so it's kind of like what we saw with printing. You have a basic function called write, which just writes data to a file. Then I can have a more complicated one which can format it. I can tell it I want the numbers to have a decimal point and 2 digits after them. I can create more complicated programs built on the lower level layers. So a layered design, or I can even actually, like, let's say I designed the layer. I could say the lowest layer is going to have a function called write. Now you guys are going to write that function. You other guys are going to assume that function already exists and use it in your programs. And I'll tell you how the function, what its input and output are, what parameters it gets, and what it returns, what it does. But I haven't yet written it. But so these other people are building the higher level layer at the same time as the other people are building the lower level layer. But each one knows that they have to facilitate those other functions to work. The lower level has to facilitate the upper, and the upper one can work on the assumption that it works. Kind of like, yeah.
Is there a possibility of skipping a layer? So that, let's say if you have.
Yes, like layer 5 could jump to layer 2, let's say, to get a service, yes. But again, it's a possibility. You could have a system design where it's not allowed. But theoretically.
Is it possible maybe that we take a 5-minute break, just because we have a little over an hour to class?
Yeah, an hour left to class?
We have till, I think, until 11:45.
Yes, let's take a break. Let's take let's take the where are we here? That's security. Well, kind of well.
Yeah. You guys have to set up. We have to set it up. Okay, go to that.
We have to buy a microphone.
Yes.
No, I can't fix a microphone.
One. Send it to your email. Open the email and see that. Yeah, but there's a way you have to set up your card.
Yeah, yes.
No, you're allowed to.
It's not.
You have to set it up. Go to like.
Not in Sylvania right now.
You try to teach them to guys.
Yeah.
I don't know why.
So I walked through, it, I had no idea how to use it, like Brian just told me, buy 50 credits.
Not-
I'm like,
so
okay, I did, now
This,
what?
you wrote this on your own or it gave you this? So like it didn't do that.
If you want to confuse it, how do you?
No, you have to, yeah, but you have to set up your card and have it.
Oh, so
You can't do it real.
like mine, let's say, well, obviously everything's
I
different.
used to use it.
No, now I'm using visual studio.
Buying credits you do everywhere.
So the way that
And you have to.
Right, so the way Doxygen works with this,
Go to,
it gives you the suggestions.
Oh, you're there. Generating.
That's
weird.
I think it says, here it says it's supposed to. Oh,
Really, reload the.
Yeah, it kind of does, but like not as like. You have to press enter. Maybe that may-
Turn off the recording.
like, look, here, ready?
Log in.
I just did that, I just did
I know,
backslash things and this is what popped up.
So if you log in, then like,
Okay, we're recording. Yeah. Now we're on to the topic of microkernels. So we started to think about it, we started with like very big kernels. Here it's like the whole kernel one program. Even here, we're also calling this monolithic, but it's has some parts that are not in the kernel, like the device graphic. That wouldn't be in the kernel. That's what's showing here. Also the compiler and all that, well, that obviously kind of is not in the kernel. This is basically the way traditional Unix is. It says traditional Unix system. Now, this is pretty much the way Unix is. There's a debate I was reading about this. And some people say Unix is monolithic, some people say it's not monolithic. Seems the right answer is it is monolithic, more or less. More or less it's monolithic. Because it's one big program. It's not layered. And then there's something else called a microkernel. The idea of microkernel, like as the name suggests, it's small. The idea is just put the essential things that you need to have in the kernel, nothing extra. Move as much from the kernel into user space. They give an example of something called Mach, I don't know.
What's user space?
User space means programs that the user runs himself, can run himself. It's a good question. I'm not sure whether the user space and there's the user mode. User mode means that it's running with permissions of a regular user, not with super user permissions, not with the kernel permission.
But saying like, what is like, try to, like, the things that require higher level access, like try to minimize that as much as possible.
Exactly.
Why? Because it uses more, what?
Because, why? A good question. Why? Well, I think the answer is because we want to have an operating system in as little space as possible for some kind of for efficiency, for some kind of small machine maybe. And we don't want to have anything extra that are going to slow us down and maybe you don't need. And if the user wants to add it, he can add it. It's in user mode. It's in his realm to add it. It's kind of like the example that I gave before of how when you download this WSL Ubuntu, it doesn't come with a compiler because it doesn't know what your plans are. It knows that you're intending. It does know one thing. You're not a standalone operating system. You're on top of another operating system, or you're inside another operating system. Not on top, inside other. But therefore, it gives you as little stuff as you could possibly want. And if you want to add it, you can add it yourself. So that's kind of the idea of micro. Like if you know what a Raspberry Pi is.
Yeah,
Yeah.
I have.
Yeah. So you may want to have a very small memory. I don't know exactly what the memory.
It's very small.
Right. So you may want to have a very small kernel. You don't want to have. If it's a big program, so a big program, theoretically, at the simplest level, the whole program needs to be in memory. That means the bigger the program, the more memory it's going to take up. So we want to minimize the operating system so that it takes as little memory as possible. Here it says benefits. Easier to extend a microkernel, right? You can always extend it. Easier to port the operating system to a newer architecture. I guess because it's smaller, there's less code to rewrite, there's less stuff to change. More reliable because there's less code is running in kernel mode. I see here he says what I was thinking, that the microkernel, when it says user space, it means user mode. There's less stuff that's running in user mode. Or significant performance overhead of user space to kernel space communication, right? As there's more communication between, you just keep switching back into kernel mode and user mode. And that's going to cost a certain overhead. Microsystem structure. So here you see kernel mode, user mode. So even the device drivers, which usually you think of being in kernel mode, are in user mode.
Why would it have more switching? Isn't the fact that most of like other functionality or whatever is given to the user, then we wouldn't need the kernel as much? The user can do more, or the point is that it's so minimized that it will need more add-ons.
Well, he has these arrows here for messages, right? So I guess if the file system wants to communicate with the application program, in other words, I want to write to a file, I've got to switch into kernel mode and then back into user mode again, and then back into, okay, keep switching, again back into kernel mode to get the message back from the file system. There'll be more switching. Whereas if I'm all in kernel mode all the time, then I just stay in that mode. I think that's the basic thing. Modules. Modules is, so here, modules is implemented in Unix. So what is it in Linux and Unix? They're both operating systems. They both pretty much run the same way. So what's the difference? So Linux is a version of Unix designed for a PC. PC is a particular kind of computer, right? What all of you have except the Mac. It's an architecture, specific architecture. Now, Unix was not originally designed for PC. It was originally designed for other kinds of computers, other architectures. Solaris is a company you've probably never heard of, but it's another company that makes computers, makes hardware. And they have their own version of Unix for their computers. And their design is modular. Linux is not. They're both Unix. They're both kinds of Unix. So what is modules? Most modern operating systems implement loadable kernel modules. It uses object-oriented approach. Each core component is separate. It's kind of like layers, but it's not necessarily that the communication is only vertical. It's only downward. It could be the communication is in any way. That's basically the idea. Whereas each module has a certain responsibility. Each core component is separate. In other words, there'll be a module that deals with devices, a module that deals with scheduling of tasks. There'll be different modules. Each talk to others over known interfaces. In other words, instead of calling I guess I'll have an interface will ultimately be a function call. But I'll call maybe a sort of a wrapper function, a bigger function that will call the little functions in the module. In other words, there has to be an interface. It says each talks to the other over a known interface. So there has to be, what does it mean talking to? I want a service, I got to call a function. So I want to call some kind of function. That's the interface. But the inner workings of that module, I won't know about. If I want to, I'll have like something, a package together of a lot of functionality, and I will have an interface. It'll give me a limited, controlled way of requesting information or requesting services, as opposed to accessing the lowest level functions. If you think about it, this is really because you have a group. You want a group of programmers that are working on this software, and you want to divide up the work. So you say you'll do this module, you'll do that module, and then before you start working, you'll say, what will the interface look like? How will I get the services that I need? So the first thing you do is you design the interfaces. And now as we're working on module A, know how to communicate with module B, even though B hasn't been finished. And I'll just write my functions and I'll do, anytime I need to use module B, I'll use according to the interface that we predefined. Meanwhile, the team that's working on module B is busy making that module and implementing that with lots of little inner functions. So it allows, I mean, there's two things it does. One, it's a certain design of the operating system that allows me to then replace that module later with a better version of that module, perhaps. It also allows me to divide the work among different teams. If you have I guess Linux was originally written by like two very smart guys, and so they just wrote it. So they didn't need to have teams, they didn't have teams, they just were really smart, and it was not so complicated as it would be now. So it was written in more monolithic. Overall, similar to layers, but with more flexibility. Well, I explained what the flexibility is. Any module will call any other module. There's no restriction of downward motion. But there's a benefit of that downward motion. I wouldn't say it's better. The conceptual beauty to this layered approach, that each outer layer relies on the inner layer. Is Linux a monolithic kernel? Most would say it is, even though the modules make it easier to modify. Most would say it is, even though the modules make it. Right. It's easier to modify than a normal monolithic, and it has modules, but it still has some monolithic qualities to it.
Wait, so why is it easier? What did you say it's easier to modify?
Well, module, yeah, like I said, I looked at what people are saying, and people seem to be saying that Linux is monolithic, even though it has modules. So that seems to be a contradiction in terms. Right, but maybe the modules only perform a small part of the task, and most of this module is monolithic. Maybe the way, I don't really know. How Linux specified. But Linux does have modules. Okay, here is the Solaris module idea. And you see there, there is a core Solaris kernel, which then requests services. Let's take a couple, for example, device and bus drivers, right? It wants to communicate with a USB card or something. So it has a special module that deals with all the USB communications. And then if it wants to talk to a file, it has a file module, scheduling classes. It has a section of the operating system that deals with the scheduling of the CPU. All right. Most modern operating systems actually are not one pure model. I guess that goes back to what I said about Linux, what it is. Hybrid combines multiple approaches to address performance, security. Linux and Solaris kernels are in kernel address space, so they are monolithic operating systems. The whole kernel is in kernel space. Plus modular for dynamic loading of functionality. In other words, these functions that deal with, file systems are not necessarily loaded when the kernel runs. They're only loaded when they're needed, as needed. Windows is mostly monolithic, plus a microkernel for different subsystem personalities. I'm not sure what that means. That might mean exactly what we just did with the WSL. That would be that's a subsystem, right? WSL is Windows. That would be what I told you to install on your PC is a subsystem, a Linux subsystem. So maybe that is a microkernel version. That's a type of Linux that's very small. Or maybe it means when, I'm not sure. Maybe it means when Windows is running, it's using a microkernel to run the Linux. Not sure. But it's just telling you that most systems are hybrid.
Can I ask a question?
Yeah.
What's a kernel address space?
Kernel address space is those addresses of memory that only the kernel can access, that only the operating system can access. Remember, any function is in memory, right? It somewhere has an address. if I wanna access, how do I access a function? I go to its address. So if that function is in kernel memory. It's a good question, and I'm giving you an important answer, which is that,
What was the question again?
question is, what is kernel, what did you say, kernel address?
Kernel address memory, it's on the slide.
Where do you see that?
So it's
Kernel or in a kernel address space, yeah. It means like this, every program has its own address space. That makes sense, right? If I don't know if I have a picture of that. Oh, we'll have it in the next slide, in section 3, we'll have a picture of it. But each program, I run 6 programs on my computer, each one has its own section of the memory. That's its address space. I'm restricted from accessing the memory. The kernel will restrict me from accessing the memory of any other program. Each program has its own memory space. The kernel itself is a program. It has a memory space associated with it, where its programs are there. If all of its functions are in its memory space, then only the operating system can access it. If, however, some of its functions are in unrestricted memory space, then any function can access it.
They can access what's not in the restricted area.
Who's that?
You said anybody can access it.
Anybody can access it if it's not in the restricted area, if it's not in the kernel addresses. Now, there's some of the kernel's functions are not in the kernel's, it is in his own address space. He has a separate, he's not restricted, he himself chooses not to restrict access to that memory space. So Linux and Solaris kernels are in kernel address space. Now, the whole kernel is in the kernel address space. So that's the definition of monolithic. That's why they're called monolithic. There are some modules that are not in a kernel address space, and they're dynamically loaded. I can't talk about it too much. Okay. I don't want to talk about Mac OS or iOS. We talked about this here, core dump. Remember we talked about this? Debugging. So I skipped a little bit. These are just examples of operating systems, which I'm not an expert on all these different operating systems. I can't really tell you too much about this. I don't want to talk about it. So we talked about operating system debugging. I already explained to you about core dump.
Core dump?
You see it says here in blue, core dump?
Oh, yeah.
Core dump is where you write down on the operating system when the program crashes, it writes to a file all of the values of the data in the memory, all the values of the memory. So you can see what happened at the moment of the crash. You can see what were the values in all the registers and what was the value in the memory. So a core dump is the memory and registers of the program, of the process. But if the operating system itself crashes, you can have a crash dump. Same as a core dump, it's just when I'm talking about an operating system. Now there's this Kernighan's law. This is a programmer from a long time ago said this. He says debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are by definition not smart enough to debug it. Because you write very, I thought it's a clever way I can use the ternary operator here, and I can use some unusual feature, and I can do all kinds of funny things, and it'll all work. And then it doesn't work. And then go figure out where you made your mistake. So you say, if you write it as cleverly as possible, it's a lot harder to debug it. The solution is keep things simple, have small, short functions. Functions shouldn't be too long. Why is that here? Just talk about debugging. So there's a function called top in Unix, which shows you which are the hogs, which processes are hogging the CPU. And you can, while the system is running, you might fine tune it, or you might kill processes. You're familiar with that from task management,
Wait, which processors are hogging the what?
the CPU. Okay, system boot. I think we talked about this. Did we talk about system boot? I explained to you last class. When the system, how it has to have a bootstrap program to tell you where on the disk the operating system is going to load it. And the small program, a small bootstrap loader, which is in ROM or EEPROM or double EEPROM. The EEPROM is, we talked about this also in architecture. Electrically erasable, programmable, read-only memory. And here it says sometimes two-step process where a boot block at a fixed, I mentioned this to you also, or a boot block at a fixed location loaded by the ROM code, which loads the bootstrap loader. In other words, the ROM code is very small. All it does is load a fixed section of the hard drive. And then that section of the hard drive is actually where the program is that tells it where to load from. That way you can save on having a very small ROM. It saves money. There's a common bootstrap loader, which is called Grub. And also, once you have this, it doesn't just save money. It means that since the boot program is actually on the hard drive now, I can change it. And I can put my own one, and I can alter it. So that's a common one is Grub. It allows sections of the kernel from multiple disks. That is, I could have the kernel be spread over many disks. It also allows you to have, it doesn't say here, dual boot. It allows you to boot a Windows operating system instead of your. That's it. Oh, is that it? Yeah. Okay, that's it. We have a little time. Let's start the next section. Chapter 3. Well, let's stop the recording. Stop.